This is the voltage between this electrode and that electrode. When I move this electrode, the voltage will change. This is what we do in DCVG. So in this position we have a voltage of 8.3 millivolts. If I move this, we will now have a negative 44.7 millivolts. I move it again, and we have negative 9.7 millivolts. I move it again, and we have negative 49.5 millivolts, and this is shown on the recording here, and this will be logged on here against time. Here's the time, here's the number of the log, DC, and this is the value. This is millivolts, and it's on automatic. Right, now I will move this to another position, and we will say a different voltage. If I simply change the positions, we will then get a positive voltage. So let's try that even more extreme. And we get a bigger positive. This is without the transformer switched on and without the switching. So this is just the setup as found, or some people might call it natural potentials, between the two, between this and between that. That means that is the potential difference between the electrolyte at the tip of this and the electrolyte at the tip of that. That's all it means, and that's all we can judge. Now the oscilloscope is connected to the Alexander cell, which is a corrosion cell, which is actually corroding. And I haven't found out yet how to set this to microamps sensitivity. I think it's probably restricted to microvolts from what I know of oscilloscopes. So this at the moment is showing the electrical changes that are taking place, and there is slight, I've got the scale here, 27.78 millivolts, and it is hovering between 1 and maybe 20, no, about 15 millivolts on the oscilloscope. I'll have to experiment with this to find out better what it can actually tell us. Right, now I'm going to move the two half cells again, but this time I'm going to put one of them on the anode of the Alexander cell. So this is now on the anode of the Alexander cell, and it is showing positive. This is positive to this, which is on a piece of the ground. Now if I move this to another piece of the ground, the reading will change. And if I move it to yet another piece of the ground, the reading will change again. Now, I will move this electrode over the cathode of the Alexander cell. And the reading has changed yet again. So from the cathode to the anode, there has been a shift which is recorded here, and if I move this, there is yet another shift, and if I swap, if I put this over the cathode and this on the anode, exactly replicating the requirements of DIN 50918, where the electron must be close to or at the interface between the electrolyte and the anode of the corrosion salt. But this is not a reference position. It's not a reference electrode. To be a reference electrode, this has to be in closed circuit. So these readings that we're getting here are invalid according to electrochemical theory. They're not what is required. And as you will see, if I change them over, then the values will reverse. Change them over again. You can see all of this has been recorded on here. So we're examining DCVG, which is the voltage between two copper sulfate electrodes. These are not reference electrodes, and they cannot be reference electrodes unless they're set up in a laboratory under closed circuit conditions, and these are not. Right, the next bit of this isn't very good. No, I haven't got this arranged terribly well here. Better. You can see that it's recorded all the movements that I've made. Now on here, this should be recording on this where it is positive, this is corroding. When I take this off, it stops corroding. Now I can't get a result on the oscilloscope, so I don't know how to set that properly. So we'll ignore that for the moment. And this part of the Alexander cell is corroding, and that is the cathode which is not corroding. When I put this back on, this is the electrolyte, and we have a negative reading. So we have a negative reading here, and it's dropping. I don't know what caused that, but this is corrosion current is shown on here, and the negative reading means that it was being protected. So in other words, the corrosion was being stopped. Now, the corrosion is continuing now, And this is the value of the corrosion current passing from the anode of the corrosion cell to the cathode of the corrosion cell. Now what I'm going to do is I'm going to switch on the cathodic protection. And we'll be able to see the effects on all the readings when I switch this on. Right. Now we can see the immediate drop when I switched on there. And I will put the timer in place. Like so. So now I switch the timer on. Now we can see the effect on the corrosion in the oscilloscope. Yeah, so it looks like it's all systems go. The only one we need to switch on now is the voltmeter, which is measuring the voltage in this battery. Now the breadboard is connected to ORAC and is connected to all of this, but it doesn't seem to make any difference when I take the battery in or out. So I take the battery out and you will see that this slowly starts to drop because of the capacitance of the system somewhere, God knows where. Right? When I put this back in, you will see that that increases to the level of the potential between here and here. So, that is all switched on there, and now I will take some photographs in front of the camera. And I'm now taking some photographs for the presentation so that hopefully we can get some of these readings and measurements actually photographed. The voltmeter and ammeter on the transformer rectifier are not moving at all, and this is because of the very, very small amount of current that's required by the system. So I've set the voltage at, it is about 3 volts, 2.5 to 3 volts. And so that is the driving force which is energizing the system, but there's very, very little current demand because of all the resistances and the circuitry of the system. And this is exactly the same in the field with the cathodic protection system. If you had a perfect coating, there would be no current flowing. So I'll now take a few more pictures, hopefully, of the readings. And some more pictures of the complete setup. The problem is with the reflection onto the photographs from all these screens, you see, because they're not non-reflective screens. Okay, so hopefully, oh yeah, a moment. Put these now. Now we can see here the effect of the this is showing the cathodic protection system stopping corrosion, and this is recording it, and this is recording the corrosion current and the changes in the corrosion current. You can see that the cathodic protection is sending 70 or something or other, and when it's off that is dropping right the way down to a positive number and then back up again. And you can see this recorded on here between these two half cells, and you can see it recorded on here on the oscilloscope. So this is the voltage when it's protected, and that's the voltage when it's not protected. The reason why these lines are so squiggly is through interference. I'm not too sure how I can get rid of that, but I'll have to try. Right, more pictures. And I'll change the position again of the electrodes. Put this one over here. Oops. Went out the way over there. And this one went out the way over here. So we've got an entirely different reading here. And you can see that both of the electrodes are out of the influence of the switching of the cathodic protection system. Now the reason for that is that the connection to the cathodic protection system is here through the Alexander cell to the pipeline. And the plates on the bottom of the Alexander cell complete the circuit. So if I move this closer here, we will get a higher reaction, as you can see on here. So if we move this closer in, still, oops, you can see the effect on here, and you can see the effect on here, which is from the corrosion current itself. So I think that's enough data to be able to start absorbing the implications of this data. This one is saying that it wants to go to sleep. This one is, oh, it's this one that wants to go to sleep as well. So I'm switching them all off. I will now try to make sure that I save all this information that's stored on here. So, save. Okay. Save it as there. 20 D O 709. Okay. Save that. Hopefully I've saved that. Now let's try and save this one. Well, I think this saves automatically. Ooh, what happened there? Oh, that's interesting. Haven't seen that before. Right. Look, I wonder if the film could show this. This is the actual corrosion on here that's taken place. Remember, this is never polished. This is the cathode. This is polished before each time of use, and you can see the very small amount of corrosion that's happened during this very short time that we have been actually undergoing the test. Don't forget, a lot of the time of the test this has been protected. So there'd not only be corrosion current flowing from here, but there'd be cathodic current flowing onto this from the cathodic protection system.